So this is a this function is on the bottom of the Introduction to Critical Points worksheet. And I just wanted to run, I did this one in class on Thursday, but I also wanted just to make a video of it so you can go back and look at it later because I wasn't recording my lecture in class. So go from start to finish. Basically what we're going to do is we're going to employ the first derivative test to find out where it's increasing and decreasing and therefore find the max and mins. And we're also going to employ the second derivative test to find inflection points and where it's concave up and concave down. Then we might do a little bit of algebra to figure out some more stuff like along those lines. So first derivative test, of course, for the first derivative test, you have to take the derivative. So when we take the derivative, we get 2 plus 2x to the negative 1/3. That's nice. And then the next step in the first derivative test is to set it equal to 0 and check for points of undefinedness. As we're really looking for critical points. We're really looking for extrema. So, and the extrema occur at critical points. And critical points are the points that make the derivative 0 or undefined. So I can tell right away that 0 will make that undefined because this is 2 over x to the 1/3. So I'm going to put a 0 in here. I'm going to put a little asterisk there to remind myself that it was undefined and not 0. And usually what that means is I want to check back and see if it's undefined in the original function. In this case, it is defined. When I plug in 0, I get out 0. So that's that works, which means this is more likely to be an actual extrema. Okay, so that makes the derivative undefined. We also want to know where the derivative is equal to 0. So I'm going to go like this, and then go like this. If I multiply by x and subtract or divide by -2, I end up with -1 is equal to x to the 1/3. So then I just cube both sides and I get -1 is equal to x. Again, I go like that. And -1 cubed is still -1. So that means -1 is a critical point because it makes the derivative equal to 0. And there are no other critical points. So this is the only places where it can change from increasing to decreasing. Now we've got to check what is it doing. So to the left of -1, I'm going to plug into the derivative because I'm testing for slope. So if I plug in, say, a negative 100, for example, now this is going to be a fraction that's negative. That's going to be a whole number. So this would be like 2 over the cube root of 100. That'll be smaller than 2 because it's 2 divided by a big number. So that means this is going to be positive. Between -1 and 0, I put in something really close to 0, like a -0.1. That's going to make this bigger because I'm dividing 2 by a small number, which will be really big. So this will be a big negative. That'll be just 2, so that makes this negative. And then finally, I'm going to plug in a big positive number, which that means everything's positive, so it's positive. So this tells me that it's increasing from -infinity to -1 and from 0 to infinity. Also tells me that it's decreasing, and by it I mean the graph. And if you've forgotten, increasing means that as you go from left to right, the y values are getting larger, and decreasing means that as you go from left to right, the y values are getting smaller. So decreasing from -1 to 0. Okay? Which means that we have, because it was going up and then started going down, we have a maximum at -1 something, and because it was going down and went back up, we have a minimum at 0, something. So the somethings we go back over and plug it into the original function. So to find out so 0, that one's the easy one because you just get 0, right? So 0, 0 is the minimum. If I plug a -1 in there, I'm going f of -1. That would be -2 plus 3, because the -1 would be squared. So that's 1. So -1, 1 is the maximum. Okay? Now, so that's what the first derivative test tells us. So this is the first derivative test. Really, this is kind of the engine of the first derivative test. And this is the information that comes out of the first derivative test, where it's increasing, decreasing, and whether it's a max or min. Okay? The second derivative test means I take the second derivative, which that's just going to be, the 2 will be 0, so that'll give me, I already forgot what it was, -1/3 times 2, so that'd be -2/3 x to the -4/3. Just the power rule. Set that equal to 0. It'll never be equal to 0, because this is really -2 over 3x to the 4/3 power. So there's no way to make that equal to 0, because the top is always -2. However, it is undefined at 0. So my second derivative test is just going to have a 0 on it. And I get a check to the right and left of it. And before I even begin checking, I notice that this is always going to be positive on the bottom. That will always be negative. So this is just going to be negative everywhere. So this thing is concave down everywhere, because remember, second derivative test gives us concavity. Well, actually not everywhere. I guess I should be careful with that. It's concave down from -infinity to 0 and from 0 to infinity. Okay? Nice. So then if we were to draw that thing, going a little bit by memory here, remember that there's a minimum at 0, 0, a maximum at -1, 1. And it's going up, 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 and down, 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 and then up, 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 up. But it's concave down everywhere. So I can see this pretty easy. And I can increase and be concave down pretty easy, like that. Notice that makes that a cusp, which works, because remember, the derivative is undefined at 0. So we expect there to be a cusp. Okay, and so notice this is going up and still maintaining that concave down. This is going up for a while and then down, and also concave down. Now it looks like it's either got to cross again or go flat, and it's got to cross because it's concave down. So let's check and see if there's another x-intercept somewhere. So we go back up to the original function, and we set 2x plus 3x to the 2/3 equal to 0. Now obviously 0 is going to work there, which we already knew that. But if we can factor out an x to the 2/3, which is maybe kind of a weird thought for some of you, that would leave me with 2x to the 1/3 plus 3 equals 0. So that gives me 0, and so then I just got to find this one, 2x to the 1/3 plus 3 equals 0. That means 2x to the 1/3 equals -3. X to the 1/3 equals -3/2. And finally, x equals 3/2 cubed, which would be -27/8. So that's about 3.5. So we go over here, and that looks like it makes sense. So it would cross right about there. And our assumption is just keeps going down. And this just keeps going up. Now what would be, I think, a good exercise for you is to grab your graphing calculator and graph that original function and see if it does look something like that. So there's the second derivative test. We took the second derivative, set up the little number line, checked in, we plugged numbers into the second derivative. One number that was to the left of 0 and one number is to the right of 0. And found out that it's negative everywhere. We actually didn't plug them in. We just could tell that it's always negative, but you know what I mean. Okay, so that is using the second derivative test first and second derivative tests and a little bit of algebra to sketch the graph.